Okay, so we can't really talk about energy management opportunities without talking about the low-hanging fruit. The things that are really easy to go out there and find to save money. The first of those is always lighting, right? We go into a facility, we see that, there are opportunities to change out the lighting usually. The next one is what we will talk about today is motors as an energy management opportunity. So motors are very lucrative for a couple of reasons. Changing out motors give you first of all the ability to control those motors if you're switching to a variable speed drive, and also high efficiency motors exist, but they are so lucrative because um, if even if you're saving just 6% or 8%, it really adds up because motors run for so long. So there are a lot of motors in a lot of industrial facilities, and they run a lot. So a super premium motor that is energy efficient and then some, another 1% efficiency gain, is going to far outweigh the capital cost if it runs for 5,000, 6,000, 7,000, 8,000, 9,000, 10,000 hours a year. So that payback is very, very short, and it's a very attractive energy savings method to do. So your low-hanging fruit, the things that you do first: lighting, motors. Motors are often replaced in an entire facility for those energy savings, not just before end of use. So now there's there used to be planned maintenance. Now there's energy maintenance because of energy plans. So now planned maintenance and energy management are sort of going hand in hand. And it's critical to know that you can save a lot by changing out your motors for high efficiency motors. So here is a efficiency versus output of some motors available, and again you can see that they're close on that chart, but the thing is, when you are adding them up, the sheer number of hours of use of your motors is where you get those dollar savings. So let's take a look at an example where we are where we're going to see those energy savings. And here you have an air compressor, and it runs 365 days a year. At full load, runs all day. That motor costs $1,400. It is 90% efficient. And electricity cost is $7 per, the demand cost is $7 per kilowatt per month. The energy cost is 5 cents per kilowatt hour. So let's look at how much does it cost to operate that air compressor for a year. How does that look compared to the initial purchase price? How much are you spending on that compressor for a 10-year period? And let's look at that compared to the purchase price. So what this is going to show us is it worthwhile to put a capital expenditure into motors? And what I'm trying to illustrate is, because of all the operating hours in an industrial motor, it's the purchase price or the replacement cost of motors is somewhat negligible. So let's go ahead and solve this one. I think what I'm going to do is first pause. I'm going to pause for 5 minutes. I'm going to pause for you to think about the factors that are going into this. Think about the units that you would use to solve this problem, and see if you can scratch out the answer to this, knowing what you know about the economics of energy savings so far. Part A of this question is asking how much does it cost to operate the air compressor for 1 year? So let's see, part A, how much does it cost to operate that for 1 whole year? So what is the total operating cost? The total operating cost is going to be that demand charge plus the energy charge, right? So we have a $7 per kilowatt per month of demand, and we have 5 cents per kilowatt hour. This is an energy. This is an energy cost, and this is a demand. This is a demand cost, right? So we would have an annual demand charge plus we would have an annual energy charge. Or an energy cost. All right, and the demand charge, we remember that that would be our electrical load. It would be how much do we get charged for that electrical load each month, and how many years would we be doing that? So you can do this with me. So from our question, it's a 40 kilowatt air compressor. It's going to operate at full load, but it's derated by its efficiency, yes? So it is a 40 kilowatt compressor derated by the efficiency of 0.9. And that costs oops. That cost is $7 per kilowatt month. Times 12 months in every year that it's going to run. So this would be, then our units nicely work out here per kilowatt, months, we'll end up with dollars per year here, which is what we would want. So if I calculate that, it would be $3,733 per year. So just our demand cost for a 40 kilowatt air compressor, that's 90% efficiency. Just that demand cost alone is going to be close to $4,000 a year. But then there's going to be an energy cost as well each year, right? And the energy cost, that's going to be up here. It's the 5 cents per kilowatt hour, remembering that energy is we use a bucket of energy. And oopsie. And we're going to use a bucket of energy, and we're going to pay, and we're going to use that over the course of a time. So we're going to multiply by time. I just have a question actually coming from a classmate saying, what kind of load did you write as the first term in the annual demand charge equation? Annual demand charge. I put just the electrical load, the load of 40 kilowatt, because it's a 40 kilowatt motor. So that is That's the power of the motor. And then in this energy cost, now I'm going to put that load again, which was derated by 0.9, right? So I'm going to put that load again in kilowatts, and then I'm going to multiply that by the use, kilowatt times the number of hours that I'm going to use it per year, times the cost in dollars per kilowatt hour, which is dollars per energy use. That load again is the 40 divided by 0.9, which is 44.44 kilowatts, times the number of hours, which was 8,760 hours, because it's running 365 days a year, 24 hours in a day. So it'll run 8,760 hours per year. And you get charged 5 cents. We get charged 5 cents per kilowatt hour, yes? All right. So that is going to be an additional 19,465. An additional $19,465 per year to run this motor. So if I were then to do the total cost is going to be demand plus energy cost just to run it, then I'm going to be at 3,733 plus $19,465 per year. Excuse my units here. 19, what is that going to be? 23,000. So we'll be around $23,198 per year. Okay, so now comment on this cost compared to the initial purchase price. Let's see, what was our purchase price? Purchase price in the question here. Let's see, it cost $1,400. That's quite a lot of money, 1,400. And so we bought this motor, it cost us $1,400. And in order to run it for just 1 year, it cost me $23,000 just to run it. So how many times more is that? Therefore, running the motor costs, I don't know, 15 times? 15 times the cost. All right, so this is just an illustration of, wow, when I make a purchase of a motor, it's really insignificant that it costs $1,400, because I run motors for so long in an industrial facility that it really becomes sort of negligible, the purchase price. So if I can squeeze any efficiency savings out of this motor, it's probably going to be worthwhile. Part B just says, how much is that going to cost for 10 years? And of course, then that would be the annual cost times 10 years. Oops. So that'll be the annual cost in dollars per year if we were to do our units correctly, times 10 years. And you would end up with, of course, $231,980 to run this equipment for 10 years. That is around, well, it would make sense, 150 times the purchase price. Okay, so in conclusion, motors are cheap to buy, motors are expensive to run, making them a very good energy savings opportunity.